Okay, random variables, we all know what a variable is. Yes. What is a random variable? A variable that is random. So every variable in statistics is a random variable. What is the purpose of a variable? We know what a sample space is, hopefully. Do we know? Yes, a sample space contains a set of all possible outcomes, and we can create events from that space. And a random variable simply takes outcomes from omega and puts it onto the real number line. So if we want to be more precise, it doesn't necessarily have to be full sample space, but part events that we could form in the sample space, you can map it to the real number line. So I'd like to say when I see this, I'll immediately know it's not the entire sample space that I'm mapping onto the real number line. Rather, I'm taking some parts of it and mapping it to the real number line, which would be the event space. Use the letter E, I believe, so I'm going to stick with E. So based on that, what would be the probability of that random variable X? What would it do? All real numbers within the sample space. Okay.
That would make the real numbers to be between 0 and 1.
Exactly. So it is going to take all real numbers that are possible for, X, and then it is going to map it directly to 0 and 1. Because we know that the probability of an event would always be between 0 and 1. With me so far? Yes? Just have to let go. So probability of X would simply take the values that we mapped here onto 0 and 1. So X in and of itself is a random variable, so we have to give it numbers. So let's take a simple example. Let's say we roll 2 6-sided dice, and X would be the sum of the dice. Good. Now, naturally, the sum of the dice would be real numbers, specifically speaking, discrete numbers. So this would be a discrete random variable. Why do we call it a discrete random variable? Because they are integers. The values that X would take are integers. So we have a specific case of a rounded variable, which is discrete, and then we have continuous, mixed, and so forth. We will talk about them one at a time. So this is the first thing I want you to do. I want you to go ahead and write the sample space for the original experiment, which is rolling 2 6-sided dice, and then the possible outcomes for X. But how do we do it without writing all possible outcomes?
Well, the smallest possibility is 1 plus 1, so 2 is the smallest. Biggest is 6 plus 6, so 12 is the biggest.
The 12 is the biggest, but you know, well, I'll wait until we get to the probability. So let me go ahead and write out the entire sample space. So my hand hurts. There is a reason why I mentioned that. Going back to the question, instead of writing them all out, we could have figured this out in some way. Oh. 6 times 6, what is that, Casey? No. What's your name?
Sydney.
Sydney.
There's 6 possibilities. We can roll the first one, and there's 6 possibilities.
That's with replacement. 6 possibilities for the first one, 6 for the second one. In total, we have 36. Every single probability that we will find, we could simply use counting to come up with the probabilities. So, what are the possible outcomes for X? So, the possible values for X are 2, 3, 4, all the way up to 12. Good. I am going to use the notation that the textbook is using, so I think they're using K, so we'll stick with K. So K would be all possible outcomes that we have. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good. We want to find the probability. Well, could only happen once. How many ways could we get? 3, 4, 5, 6, 7, 8,
Right.
I didn't even count because the distribution is metric. Oh, I just threw that word out. If I add all the values, what should we get? 1. If I add all of these probabilities, I should get 1. So, 36 out of 36. So what we have right here is what we call the probability mass function. So PMF, probability mass function. If you're Catholic, you'd like this. Huh? Exactly. So this table that we've summarized for all possible values of x would simply be the probability mass function. So what did we do? We had an entire sample space. We created a random variable, which, is an event of some sort, definitely some of the dice. So we took this and we assigned values on the real number line. So it was that step, event to the real number line. And then we had probabilities where we take whatever values we had on the real number line onto 0.1. So these are the values on the real number line. They get mapped to the interval 0 to 1. Does that make sense? So 3 binary digits are transmitted in sequence. The receiver on the other end records the maximum of the 2 digits that arrive last. So we want to find the PMF of X. Okay, so how many possibilities would we have? 8, 2 times 2 times 2. So first of all, so in total we have 8. And it's going in sequence, so I'm going to look at the last 2 digits only. Now, what are the possible values for X? 1, and 0. Excuse me, 0. So takes on the value 0, takes on the value 1. We've got to find the probability of X is equal to A. Well, we just have to count the maximum ones because that's all we need, right? 0, 1, 0 can never be the maximum. So how many of them result in a maximum of 1? Maximum of 1 in 1 is 1. So we're going to take 6 out of 8 for 1, which would be 3 out of 4. 2 out of 8, which would be 1 out of 4. Yes.
You use the notation here on the equal sign there. Do they do the same thing or do they do differently? Do you want to make sure that
What do you mean?
you use the x's in the set of 0, 1, and then over there x is equal?
It's not an equal to colon, but that's the proper one. Proper way to write it. X is in that set. But good question though. So do we understand? So 1, 4, 3, 4. Good. Now we have done 2 different probability mass functions. By looking at them, I want you to give me a couple of properties for a probability mass function to be a probability mass function. Do you follow my question?
Oh,
Only two properties.
oh,
Probabilities must equal to 1.
Total probability.
Oh, the total probability must equal to 1. Check. Okay. If we add all the probabilities in a PMF, it must add to 1. That is 1. What is another?
The variable needs to be discrete.
For a PMF, yes, the variable has to be discrete, correct. What else? Yes. You guys gave me 2, so I'll just shut up. So the third one, every single value that we have for probability must satisfy the conditions for probability. In the sense, it has to be 0, and it could be 0, it could be between 0 and 1, but it cannot be 1. Because if you have 1, it's no longer a probability mass function. All we are saying is that X could take only 1 value and it's certain to happen. Does that make sense? So none of these values could be 1, because if 4 becomes 1, everything else is 0. And we're saying that the only possibility is 4. It happens with probability 1. So a probability mass function is a distribution. So I will write the properties over here. So sum of all the probabilities in a PMF must equal 1. The outcomes for X must be discrete. When we say probability mass function, it implies that the random variable is discrete. There's nothing wrong in putting equal to here, but sort of is trivial when it comes to a discrete PMF or PMF. But the PDF, sure, it could take values way past the domain that we define the density over. So this countably finite set of outcomes that we have is what we call the support of the PMF. So in the previous problem, for the binary digit problem, the support was formal way of support. So for the binary digit problem, x was in 0 or x will be in 0,1 for the sum of dice. Example, it would be 2, 3, 4 all the way up to 12. The simplest experiment for a discrete random variable is a Bernoulli experiment. What is a Bernoulli experiment? Well, a Bernoulli experiment is where you have two outcomes. Two trials. Oh, sorry, just two outcomes. I'm thinking of the next one. Typically, we call it success, failure. And typically, success is 1 and failure is 0. And probability of x is equal to 1 would be equal to p. And probability of x is equal to 0 would be 1 minus p. I'm going to argue that we had already seen a Bernoulli experiment today. You can agree with me, or you can disagree. Huh? You agree? Why? What? The binary one. If I just paraphrase that question, instead of saying, find the PMF of x, if I just paraphrased and said, find the PMF of x. If x is equal to 1, it's a success. If x is equal to 0, it's a failure. Success of something, failure of something, doesn't matter. So only two possible outcomes, and one of them is favorable, the other is just a complement. So if you look at the previous problem, we had 3/4, and 1 minus 3/4 is 1/4. So that example is a simple Bernoulli experiment. Does that make sense? The simplest PMF that you can think. The next one is a binomial experiment. Once again, the reason why we want to understand the experiment is because if we know that whatever we have, whatever we are studying, or whatever experiment that's being performed follows one of these, then we can easily use a formula or, properties of the PMF and get the answer right away. So what does bi mean? Two. What does non mean? Food. Food. Just number? Or name, right? Name, number, etc. So we need to have two of something. So we can call something to be a binomial experiment if there are n independent Bernoulli trials. If I call some random variable y, then y must be Bernoulli, your book calls it burn, feel the burn of P. Now you may ask me, well, what is that squiggly sign? In statistics, that simply means distributed as. Or y has the distribution Bernoulli P. So I have n independent Bernoulli trials. What does a Bernoulli trial mean to you now that I've mentioned what a Bernoulli experiment is?
Possible outcomes equally weighted, or are they?
Do they have to be equally weighted? No. Two possible outcomes with some probability P, right? So,
E or not?
but then, yeah. Okay. P, naturally, we have defined it already to be success. So P is the probability of success. And the important condition here is that the trials are independent of each other. Good. So we have n independent Bernoulli trials, which is y. Don't have to worry about y, but we have y distributed as Bernoulli P. P is simply the probability of success. And the trials, they have to be independent of each other in the sense the outcome of one trial should not affect any of the other trials. I would like to study the number of successes out of n trials. Well, what are the possible values for x?
And 0.
0 to n. If x is equal to 0, we say that no successes at all out of n trials. X is equal to 1, exactly 1 success. X is equal to 2, exactly 2 successes, and so on, all the way up to n. That would mean that all n of them, all n trials resulted in a success. Does that make sense? So understand the experiment. So that is the experiment. This is how we define the variable. If that is the case, then we say that x will be distributed as I believe your book uses bin, short for binomial, n comma p. It's not the number of parameters. Those two are the parameters for the PMF. We are going to come up with the PMF soon, but we call it the parameters for the PMF because without the parameters, we cannot compute the PMF, or we will not have a PMF. Are we clear? Yes. Okay. Can you think of a good binomial experiment? I know. Fine.
Yeah.
Just say this case. So Frodo encounters a ring weight. Do you guys know what I'm talking about? Lord of the Rings. You should. If not, you haven't lived life to your fullest.
Yes.
So Frodo encounters a ring wraith 4 times on his way to Mordor. The probability he will escape is 0.82. So 82% chance that he will escape, which simply means that Sam was there. So let X be the number of times he escapes. So we want to find the PMF of X. So first off, we would like to know if this satisfies the Bernoulli trial. We would want to have Bernoulli trials. So at each given encounter, there could only be 2 possibilities, right? Either he escapes or he doesn't. And the probability that he would escape is 0.82. So we know P is 0.82. And the trial, how many do we have? We have 4 trials. And at each trial, we would have a success or a failure. Success would be escape, failure, not escape. So it doesn't escape. So X is the number of times out of the 4 times he escapes. So what is the support of X? 0 to 4. Now our objective is to come up with the PMF.
I have a question. In the last couple examples, you were doing the sample space and then you've been doing possible X outcomes, and now you're changing notation, so I'm a little like confused. Can you write off the sample space? Can you write off the sample space?
Yeah, so remember I used the entire sample space once, right? Take the entire sample space and map it to the real number line. In this case, the entire sample space is 0, 1, 2, 3, 4. And if I map it to the real number line, it still is 0, 1, 2, 3, 4. Right? Okay. Any other questions before we move? Yes.
If he does not escape, is that the end? Or is it like, even though he doesn't escape, he'll still encounter another one?
I don't know. At the end, Frodo goes to Mordor.
But I'm saying like, for the sake of the probability, because I'm thinking like, given that he doesn't escape the first one, does that mean that that's it?
You use the word given that. So that's a fundamental problem with binomial.
Well, what he's trying to say is like, let's say he gets caught the first time around, then does that mean he doesn't see the second, third, fourth, or eighth? I think it's because
They are independent. Right? You use the word given that. So in other words, whatever happens the first time, the second time is going to happen.
Okay.
Whatever happens the first 2 times, the third time is going to happen. That's what we mean by independent trials. So if you say the phrase that you use is given that, the moment you say, okay,
I was just using that as an example earlier. I wasn't trying to like imply anything else. I was just saying like, you know, because I was just thinking like for the scenario here, it's like, all right, let's say, you know, under the circumstance that he doesn't escape the first one, is that going to mean that that's the end and he doesn't even see the other 3, or is each one still going to?
each one's still going to go.
Okay.
Yeah, because the trials are independent of each other. We go through all n trials. Okay, so P is 0.82. Do we agree that this is binomial? Okay. So X is binomial with n to be 4 and P to be 0.82. Since they are independent, we don't have to use, you know, Bayesian rule or anything, right? So independent, we have 4 trials, in other words, 4 different independent experiments. How do we find the probability of them happening together? We simply multiply them. So since we know we have 4 independent trials, so we just find the probability and multiply them. So I want you to try and find these probabilities. Let's see if we can do it. It's just multiplication rule. So, just to clarify, the trials are independent in the sense, even if he doesn't escape, he finds some way to go and, you know, move on. You know, and then he encounters another ring ray. And then he goes and then again he encounters the ring ray. So not escaping doesn't imply his quest ends right then and there. Does that make sense? Okay, so we have 4 trials, and X is the number of times he escapes out of the 4 trials. And if X is 0, then it simply means that he didn't escape the first time, he did not escape the second time, he did not escape the third time, he did not escape the 4th time, but he went on doing stuff. So right. So that would be 0.18 raised 4. Yes. Okay. Most of you got it right, but you were close. Second case. If that escape is still confusing you, he's just wounded and then he moves on. Out of 4 times, how many times is he wounded? So exactly once escapes wounded out of the 4 times, in the sense, what would the probability be? He's got 1 success. The first time it would be success, right? So what is the probability? 0.82. And the next case? 0.18. Next case? Next case? So it would be 0.82 multiplied by 0.18 cubed. That's what you guys wrote. I am going to say that that is close, but it's not correct.
Or when it can happen.
Huh?
Or when it can happen.
John, right?
What?
What's your name? Chris. Close. Why 4 ways?
Or they just like a big one.
So I can switch this around. So, you know, wounded, escape, moves on, but second time is a success. Third time, failure. 4th time, failure. Yes. Another way for it to happen is failure, failure, success, failure. Another way to happen, failure, 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 success. Does that make sense? So 4 ways are possible for it to happen. So 4. That it's just 1 way. Good. Next case. So 2, exactly 2 times the perfect escape. So check, check. The other 2 times, not so much. Right? So that would be 0.82 squared multiplied by 0.18 squared. Yes, you guys did this. Close, but not correct. Why? Go ahead, Shane.
Just like the previous problem, there are 4 possible ways of kind of arranging the successes and failures in a different order. There would be 6 ways in this one.
Exactly. So if we're going to, you know, just like the previous one, I'm just going to move that check marks back and forth, checking the process. There are 6 possible ways for that to happen. So 6. The next case would be exactly 3. So check, 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 cross. Will happen in 4 ways.
Yeah.
Correct.
It's 1, but switch the 1 and the 0. Okay.
And the last case would be, Chris, I want you to explain that in a second. Check, 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 check. Right. Yeah. So you would have 0.82 raise 4, 0.18 raise 0. Yes. 1 way of that. I'm just doing some algebra, basic algebra here to illustrate a point. You said something, Chris, go ahead.
So for a chance of getting 3 and a chance of getting 1, in terms of the number of ways you get confidence, is the same, because you just, if there's like, if you wrote out the actual like table of the different outcomes, the one, you just switch the ones and the zeros, and you end up with 3, you turn the number of ways it happened 3 times the number of ways it happened 1 time the same.
So it's a matter of, perspective. You can just flip the successes and failures. You call it 1, 0. If I call it 0, 1, it's all going to be the same. I'm just flipping things around. So the probabilities or these numbers will be symmetric. Great. Is there a different way to write this? I say that there is a pattern here. What pattern do you see?
1, 4, 6, 4,
1, 4, 6, 4, 1. Great. And what is that? Huh? Bell curve.
It's a choose function.
Huh?
The choose function.
It is the choose function, Pascal's triangle, right? So, Nathan, how does the choose function? How do we get these values?
Well, do you mean like just the formula? It's n factorial.
Wow, I know the formula, but
Okay.
why the choose function?
Well, because you're basically taking, like for the second one, let's say, right? We're choosing 1 out of 4 places to put the, to put the probability.
So if you go back and, this is why counting is important. So if you go back and look at the question, we're saying no successes, exactly 1, exactly 2, exactly 3, and exactly 4. Now, does the order matter? It really doesn't. Do we agree? Whether I get 2 successes here, 2 successes there, doesn't matter. It's all the same thing. I get 2 successes. So now how many ways can it happen? So I have 4 choose. Let me correct that. A success is a success. It is not indexed as success 1, success 2, failure 1, failure 2. In that case, the order would matter. So here, order doesn't matter. I have 4 slots, and I'm just going to throw 2 successes somewhere in there. So that case would simply be 4, choose 2. Agreed? What would that be? 4, choose 1. And what would that be? 4, choose 0. Good. Do we understand the choose part? Okay. Still, there are more patterns. What else do you see? The powers. If you look over here, K, 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 okay, okay, okay. Get it? Yes? Okay, so there are all Ks. And what about those? 4 minus K, right? So these are simply 4 minus 0, 4 minus 1, and so forth. So I could write this as 0.82 is simply the probability of success. So P raised 0, 1 minus P, 4 minus 0. Yes? The second one, P raised 1, 1 minus P, 4 minus 1. The third, P squared, 1 minus P, 4 minus 2. P cubed, 1 minus P, 4 minus 3. The last one, 1 minus b, comma. Good with me? So if that is the case, we have a nice little pattern. We identified the pattern. I want you to tell me how I could generalize this. So, oops, probability of x equals k.
You could do n choose k
And choose k,
times p to the k power
okay?
times in parentheses 1 minus p to the power of n minus k.
Good. Do we agree? And what are the possible values for k? 0, 1, all the way up to n. So, in practice, as long as we identify the experiment and relate it to a known experiment, then we can understand that experiment easily. So if you encounter a situation and you determine that that particular situation is a binomial situation, then all you have to do is use that formula to get all kinds of probabilities. Does that make sense? Yes?
The one percent.
I'll say, thank you. Happy now? So a student has taken Professor G's class, definitely not me. couple of times. And during the classes, the professor had mentioned 25 jokes. It's the probability that the student finds the jokes to be, the probability that the student finds the joke to be funny is 1%. What is the probability that the student liked the professor's joke exactly once or exactly 15 times? Second, what is the probability the student liked the professor's joke at least once? Okay, so first, we want to know if the trials are independent. Of course, they are. The jokes are related. So, n Bernoulli trials, n is 25. The probability that the student is going to find the joke to be funny is 1%. So that's 0.01. So probability that joke is funny. And we are going to define X to be the number of times or number of trials. In this case, what is the trial? What is the trial? There are 25 trials, but what is the type?
Whether it's fun.
What did I call as a trial? Or what am I calling as a trial? The joke, right? The trials are the jokes.
Yeah.
The number of jokes out of 25 jokes that the student finds them funny, it is going to be very small. So would we agree that X is binomial? At any given trial, at any given joke, if you consider any given joke, the student's either going to say, that's not a joke at all, or laugh. The chances of the student liking it is only about 1%. So there are only two possibilities per trial, and the trials are independent. The trial in this case is simply the joke. So first problem wants to know, well, before we get to that, X is binomial, and what are the parameters? 25 and 0.01. So the first one, we want to find the probability the student liked the professor's joke exactly once or exactly 15 times. So X is equal to 1 or X is equal to 15. Or is the same as 1 union 15. So what rule should we use? Addition. So this would be probability X is equal to 1 plus the probability X is equal to 15 minus the probability X is equal to 1 and X is equal to 15. You've got to explain yourself on an exam. If you just put an answer, I'm not going to give you full credit. So what about the last term? Why is it 0? Mutually exclusive. So probability X is equal to 1, exactly 1. How do we find it? Well, we know the formula. So if I choose 1, probability of success would mean probability that the student finds the joke to be funny. So 0.01 raised 1. 0.99 raised 25 minus 1, which is 24. What, oh, yeah, sorry. N is 25, thank you. Plus 25 choose 15. 0.01 raised 15 multiplied by 0.99, 25 minus 15, you get 10. What's the final answer? 0.1964. Not bad. 19% of the time.
Well, the second term there is practically zero.
Yeah.
It's to the negative, it's 10, it's like.
What is the probability that the student likes a joke at least once? What does at least one? Zero. Okay, not zero. So I can write it as 1 minus the probability that x is 0, right? More than 1. So 1 minus 25 choose 0. 0.01 raised 0 multiplied by 0.99 raised 25. And what is that probability?
0.222, 178.
After subtracting from 1?
Yeah. It's still really low.
Thanks. 0.22. Exactly 22?
No. 22217, blah, blah, blah.
Okay, so 2222. Okay, 22.22% that he finds my joke funny at least once. Does that make sense? Yes? Okay,